Welcome back to the Demystify Sci podcast. I'm your host, Anastasia.
I'm Michael Shiloh.
And today we are talking about space, Venus, asteroid impacts, and the history of Earth and the solar system. Today with us we have Dr. James Garvin, who's the chief scientist of the Goddard Space Flight Center. And we talked to him about his work that has, over the course of his 35-year career, spanned a lot of different topics. When he was doing his thesis back in the, 70s and 80s, he was focused on the Venera landers that were sent by the Soviets to Venus, and so he characterized some of the first data that came back from those missions, and has kind of maintained a lifelong interest in what exactly is happening on Venus, which is kind of a sister planet to Earth in the sense that it should be like us, but isn't. And so he's got a new mission called the DAVINCI mission that's planning to go back to Venus with this weird atmospheric dirigible/submersible that they aim to slingshot around the sun onto Venus, dip down through the atmosphere, and then explore a really unusual mountain range that doesn't look like anything that's on Earth. So we talked to him a lot about the act of putting that mission together, about the scientific questions that they're asking, about the mysteries of doing this kind of science on a planet that is still pretty much a closed book to us, unlike something like Mars, which has been mapped really well.
We also get some really interesting 30,000-foot insight into how paradigm shifts take place in science in the modern landscape, because you've seen a few of them, and planetary science is one of those fields that's really on the move, and it's not politically pegged to anything, so it doesn't encounter the same level of resistance. So I think that we have some really cool discussion here of what it takes to make that happen and how the collaborative atmosphere evolves in a culture and in a society to lead to paradigm shifts, which is what we're always on the lookout for here.
And he's just really playful and well-informed and has a great history of anecdotes and people that he's worked with and questions that he's asked. So we think that you're really going to enjoy it. And so listen up. Tell us what you think in the comments. Come to our Discord, talk about the episode there, and tell your friends, because the podcast only grows if people know about it. And we don't really hit the algorithm in the way that more polarizing discussions do. And so your direct help can be just telling your friends about the Demystify Sci podcast.
Yeah, it really matters for whatever reason. When we try to, especially aim for these high quality guests, they really want to know how many people they're going to reach. And that's something that only you guys can make us capable of.
I think it's worth noting that we just hit 4,000 subscribers. So we've been doing this for 140 episodes now. And
at least for the YouTube watchers right now.
For the YouTube watchers right now,
if
exactly.
You're listening, yeah.
And so thank you. Thank you to all of you that listen, that comment, that have ideas, that send us guest suggestions. It has been an absolute joy to be doing this project. We have big plans for it. And so if you really want to support us along the mission, come to our Patreon or patreon.com/demystifysci. You get both episodes for the week early. You get them on Saturdays. You get to come to our patron chat. And we're gradually trying to figure out what else we can offer to patrons in gratitude for your support. So maybe drop us a line for what it would take for you to join our Patreon. But otherwise, sit back, enjoy the conversation with Dr. James Garvin, and we'll see you next time.
The scientific revolution starts now.
The Demystify Sci podcast.
Let us see in the dark.
But when we look at landscapes, particularly that are very dynamically produced, big volcanoes that blew up like Tonga Pai, which blew up back in January of 22, we've been working on that one. My gosh, 9 cubic kilometers of stuff disappeared. How does that happen? And in making large body impacts, the kinetic energy exchange leads to instant landforms. Literally, the work is done in an hour. Instead of, 10 million years to build a mountain, it's an hour or less. Now, there's other things that continue. I mean, the ground stays hot, blah, blah, blah. We can debate. But anyway, that's what's exciting. And so that third dimension, it's like that. It's like the archaeological vision of the artifact we're looking at. And then it changes. It degrades over time, becomes something else. People build condos on them, on Earth, someday on the moon maybe. And so when we look at the record of hypervelocity impact collisions, that's what we got, other than very esoteric methods involving geophysics, measuring mass anomalies, what the structure of the ground is underneath, and weird chemistry that have rocks that, don't look like normal rocks. I used to take to kids a piece of a sandstone. It's a heavy rock. It would sink. You put it in a pool. That was shocked to crap at the impact that made the meteor crater in northern Arizona. And I would take it and throw it in the pool. They could say, oh, it's going to sink. Oh, we'll never get it. And it would float. I said, well, that's shock rock. It's turned to pumice. And from an instant explosion, 15 megatons or whatever, boom, it took a rock that would sink like a stone into a floating piece of pumice in minutes. So anyway, that's a long answer to your short question, but I think the lay of the land, wherever we're going, Moon, Mars, Venus, Earth, deep sea, Europa, blah, 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 is that interface. And, we look at it in 2D with imaging of planets and, everything, and from flying over it in airplanes and whatever we do. But a lot of the hidden story is in the 3D. And the quality of measuring that 3D, how often and how finely, tells you what you can see. So, my last thing I'll say is, got a bunch of young students, young girls, and a couple of us NASA guys out to the island before it blew up in Tonga. And we took a bunch of drones, collected 4,000 images, made a topographic model of the island good to a few inches. Of course, then the island blew up and disappeared. But we had a model where you could predict where the water was going to go and what was going to break when. And so this crusade of many of us is a measurement crusade that allows us to start to look at what if questions, the kind of fun ones that you were saying. And so that's been one of the things that I have felt passionately about, because, it connects to us as people, but it connects to the physics and chemistry of how the landscape responds. And we live in a collisional universe. So this is just one scale of the collisions that we can measure. So.
Yeah, it's interesting that, 50 or 100 years ago, it seems like this idea that geology could change instantaneously was sort of anathema to the
unpopular,
discipline.
You could say.
It was unpopular, right? Because they were fighting against these religious extremists, essentially. And it feels like it's taken a long time for that to unwind. Perhaps even seeing other planetary systems and seeing the dynamic evolution of these bodies. Have you felt a change in your own lifetime in terms of accepting these more step function changes in geology, or I guess what would you call it, exogeology or planetary geology?
Well, for me, I guess because I'm a curiosity-driven geek, I hope for the exciting and the things that we don't think would happen. And so the uniformitarianism that you're talking about, that goes back to the great geologic mappers of the 19th century and before, Hutton, et cetera, they saw things slowly moving in time, recording those histories, building the chronologies of everything, not punctuated by an equilibrium that, oh my God, how do you throw 500,000 megatons at a landscape, when that amount of energy in the landscape took 5 million years to change it. And so I was glibly, maybe naively, accepting. And I think, in the late 50s and early 60s, coming from the work of Shoemaker and a few others, seeing the fact that our planet is punctuated by geologic phenomena that are dynamic extremely, which we see on the moon. We sort of see on Mars, particularly in the space age now. We know, of course, on Venus and lots of places. I mean, we're bringing back pounds of hunks of asteroids that are the stuff that collides with us this year and with OSIRIS-REx. So I was less doubtful. I was more excited about the possibility. It's kind of like when you first become aware of Darwinian evolution and all the follow-ons.
Yeah, I was going to say evolution is another one where the same thing's happening, it seems like, where people are starting to realize that these leaps can happen very quickly depending on the way the environment changes around the organism.
Right. And that's so beautiful. I mean, my son, who studies microbiology, took a class at Brown called, evolutionary microbiology, where they mutated microbes and did metagenomics and saw what happened. Basically formed new stuff. Kind of neat. You could do it in a semester as an undergrad. And that's the stuff of change. And, you could make an impact, Lord knows, not wouldn't be necessarily pretty, but experiments have been done to do that. So anyway, for me, the doubt is not so much what got me, it's the excitement of what that can tell us. The impact record is the chronometer on which we measure histories of landscapes. And on Earth, it's muddled by incredibly exciting stuff that we live with. But on the moon and other worlds, we have this, this litmus test of what happened when in a stack of things. It's kind of like the fossil record, but it's the impact record. And we're seeing that actually applies on Earth with events like the Chicxulub impact, at the KPG and the Permo-Triassic and, farther back. These events changed the natural history of life. And, you both probably know Stephen Jay Gould's books, but I always loved what he used to say. If you played the tape backwards, we wouldn't be here.
It's crazy how recent the Chicxulub impact, the acceptance of that model has been. I don't think maybe young people don't realize it, but this was amazing that people turned their minds on this, because people didn't really know how the dinosaurs disappeared before that.
And I feel like you must have been deeply involved in science on both sides of that paradigm shift, where there was the sense that the consensus grew to gradually accept that there had been this impact. Because people must have been proposing it for some time before it became widely accepted. And I wonder if you have a mental model for how it came to be something that everybody agreed on. Because I assume that, and maybe I'm wrong about this, but as you start to look at the impacted and cratered features on the moon and Mars, you must gradually come to decry the idea of Earth's exceptionalism.
Well, I think that's correct, that Earth is not unique. We are all planets in this together. It's actually a good thing, because it allows us to understand beyond our local neighborhood. And that's what science is, the understanding to be predictive. But I think your point, I suspect that the evolutionary disappearance of dinosaurs, when I was an undergrad, we talked about stochastic macroevolutionary extinction events that you could predict based on climate upheavals, changes in circulation, large volcanic provinces, like the great eruptions of Deccan and others, and as a causal mechanism that shifted too rapidly the environments in which these large land creatures, unlike the giant great blue whales of today and others that live in an ocean, couldn't adapt fast enough to those dynamics. But people always wondered, when I was in school and others, well, maybe it had to be even faster. Maybe that change had to be so dramatic, and we didn't have the smoking gun. We knew impacts were here. There were a few big scars people had studied, Sudbury in Canada, but that was 2 billion years ago. Vredefort in South Africa, really old. And the loss of the dinosaurs as a part of the faunal record is, only in the last, 60, 66 million years. And so I think there was always the tension of what could have been. And then a group of colleagues working from different areas put together a chemical evidence associated with a possible impact evidence, stitched them together, and build a model that was then testable. And when it first came out, the papers by Alvarez in the early 80s and his cohorts, looking at the iridium anomalies that probably aren't from Earth and establishing that they were not from Earth, started to get the ball rolling. And then people said, well, where's the impact? And, that's where the geophysicists came in, and the Chicxulub event was looked at. And now people like Robert De Palma, looking at exposures in North Dakota, are discovering the mega tsunamis and all the other stuff that something of that consequence, of an impact of that consequence created. And we see records of things at that scale, the Chicxulub scale, on Mars, on Venus, on the moon, on icy satellites of Jupiter. And so, this is not, it may not be common, but it's not an infrequent part of the history of these worlds. And in our world, what if those happened every, few hundred million years, as the current flux energy curve might predict? Then that might be an impact, an impulse into the history and evolutionary processes of life as we think about it. And now the microbial story is different, adaptation mechanisms at the small scales. They'll outlive all of us, and we know that. But still, I think those paradigm shifts sometimes come by, multi-perspective, not accidents, but serendipity. People looking at.
It seems like an incredible collaboration, right? It's just,
it is.
And that's and across disciplines too. Where did that play out? What did it play out in the journals? Did it play out in the popular media from these groups? Did it play out in what was the equivalent? There wasn't really any sort of social media or anything back then, but conferences. What brought all these people together?
Well, it was conferences, and I remember there's an annual Lunar Planetary Conference, and there are others, around the world, Europe, US, and in these conferences there'd be sections about, meteorites, impact cratering, and experts would talk about it, and the first connection across those would appear in meetings like that, and then papers in the more provocative journals, Science and Nature, and ones like that, started to get the ball rolling. I remember being a reviewer with one of my mentors of one of the Alvarez papers when I was in grad school, and trying to recreate some of the aspects of that and test, and it obviously made some sense to a group of reviewers, and it became exciting. It was like the excitement over the possibility that there were meteorites from Mars on Earth, which when that first came out in the late 80s, people said, come on, physics, you can't throw something from Mars, not going to come to Earth, blah, 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 God knows. And now, there's hundreds of them, some absolutely extraordinary. It's why returning samples from Mars will be so telling. But sometimes these changes come about and people are all up in arms, and then, there's a convergence. More people look at the problem from more ways. Now, in the days of instant, exposure through social media and other mechanisms, so often even unfiltered, you can get the word out before, all the cross-checking and stuff is done. And in some sense, that's the balance today of instant awareness of a possibility against the publication standards of science, where peer review is critical. I mean,
how long were Alvarez and them playing with it before it was appearing in Nature or Science? Were they publishing in smaller tier journals before that? Were they discussing it at conferences for for several years, decades? I mean, how long was the underground churn going on?
My recollection was it was a few years, and it started with identifying, these anomalies at chemistry of trace elements like iridium, which are typically affiliated with, asteroidal impact meteorites, and they were found in layers. And so why would they be in a layer? Why would sedimentary processes make them in one layer? Well, typically if something explodes and has a, ballistic curtain of stuff, it might make a layer. And that would be a nice way Mother Nature's geology would work. And so they did the correlation, said, this probably is not terrestrial. I mean, volcanoes do not produce that kind of chemical anomaly. So what is it? And we knew of some examples of that kind of chemical anomaly on the moon. Thanks to Apollo, that brought back samples. They put it together. And then the question was, where's the crater? We know lots of little craters, and then we know a couple big old, ones that are largely exposed in quarries, and they don't look like a big round bullseye like those on the moon. And so where is it? And that took the creativity, the skullduggery of the science community. Said, well, we can find them even if they don't express themselves like you might expect. And how do we do that? We use new techniques. And that's the magic of science, following the leads. It really is CSI does, does the planet, apart from the TV pun. But, and so, and I think today, the fascination over how we express science and communicate it with social media, with, Instagram Reels, that's an example, of course, with conferences, and in COVID, all virtual connectivities is exciting. And, at NASA, our job is to communicate what we're funded to learn. It's part of the process that we're supposed to use. And so it's a delicate balance between presenting a paper, but then also publishing it through the standards and the rigors of peer review, because, and that's an important aspect, I think, of how science is evolving and becoming more rapid.
Well, it's one thing we're really obsessed with here is sniffing out where those paradigm shifts are going to happen. And, for better or worse, we've only really been deeply paying attention for a few years, and we have only hints of what these deep problems are and how not necessarily what the solutions will be, but where they might appear from. We're just always so curious about what the interpersonal relationships are that make those come about, because we often hear people who feel stymied by the peer review system, or they feel like it's impossible to talk about certain subjects, and there's always we have some skepticism of that presentation, because it seems like there's so much to accomplishing anything in the world that involves forming really good relationships with the people around you. And it seems like that almost plays in as much as all of the forensics into whether the idea is able to actually come and become foundational.
Because there's something really interesting about the story of the Chicxulub crater, because you find this iridium layer, and the iridium layer needs to be explained. And in order to make the leap to an impact, you have to be open to the idea of an impact of that size being possible. And I feel like this was right around the time that Velikovsky was writing. And Velikovsky had this really catastrophic, poorly substantiated argument about what was possible. And so many people came out as an immune system of look, this is not how you do science. This is not what it looks like. And for good reason, right? Because there was a bunch of stuff in the book that has no evidence for it. And yet I wonder if people who were in sciences read that, were able to throw away all of the chaff and then take some kernel of it and were like, that stuff's nonsense, but check this out. And they were able to take that imaginative, almost fictional portrayal of what could have been and map it onto something that was realistic. And I feel like these days our tendency is to kind of lock down these sorts of wild narratives because, it's like we're always kicking at Graham Hancock because he's telling these...
Do you know Graham Hancock?
I do not, actually.
Okay. He's like a journalist turned archaeologist. He's a big advocate of these advanced civilization things.
Atlantis.
Super popular author, but the scientific community is really... What's the word? Irritated?
He makes tendentious arguments. And I think that's, to make a tendentious argument as somebody who purports to be telling a story, it's like, well, that's the baseline marker of responsibility, is the fact that you don't say more than your evidence warrants and you're careful, right? That's the baseline that you learn in grad school. That's the baseline that you learn as you come up as a scientist. But I think that what I'm saying is that I feel like there's a really, really, really strong immune reaction against fantastic stories. But the fantastic stories are also the places where we get the inspiration to be able to look at the evidence and then make the leap to what is unfathomable.
Possible but unfathomable.
Yeah, possible but unfathomable.
And I think one of the things that goes with that is, open-mindedness is important. Looking at science across the thematic boundaries where barriers occur. The physicist that doesn't want to see what the geologist is looking at in a slow process that makes a mountain, or whatever. Sometimes those boundaries, those unnatural boundaries, stovepipes, cause barriers to the communication that you're talking about. But I think the other aspect of it is daring to hope that there is a measurement solution that will do better. So daring to measure what you couldn't measure, and so now I just took a little piece of what might be a part of the asteroid that made Chicxulub, took it to a lab and did nanoscale X-ray computed tomography. I can look inside something like a grain of dust at, billionth of a meter scale. That's pretty cool. And those kind of measurement technologies, now used for many things, Lord knows, medicine, we can go through them, engineering, can now be applied to problems, with where those measurement techniques weren't even available. And so when you look at the Chicxulub thing, what made those naysayers start to look up? Well, it wasn't one layer with one chemical anomaly. It was that layer all around the world. Because some people had the vision to say, well, if it's here in Italy, maybe I can find it in China. Or maybe it's, in Australia or wherever. And by doing that open-minded search space, greater things were discovered. And then people said, well, it doesn't matter if we can't find the source crater. It's there in the record. How do we find it? It's like archaeology. I mean, when I was a kid, I got to go to Upper Egypt, way before you guys were born, I'm sure. And I went into King Tut's tomb before they moved all the good stuff. And imagine walking in, my brother and I, and mother and father, and one dude, and there's gold leaf on all the walls. And it was like, oh, I mean, I wasn't old enough to fully appreciate, but I could see the power of antiquity, in how they made great things, temples, Queen Hatshepsut and all that great stuff, but also what they left as the records of their leadership. I mean, that was pretty cool as a 9-year-old to see that. And I think, what you're saying, the exposure to ideas eliminating what might be the fantastical or not, unresolvable because you can't really test it. A lot of science is limited by what you can't test through the classic methods. So how do you find another way around that to be able to test to see if you have something that holds water? And so connecting, still controversial, connecting the history of catastrophes in the Earth record, from asteroidal collisions, cometary ones, to the history of life, was a big freaking deal in the 80s. We had big conferences up in the mountains of Utah at Snowbird. They were called Great Catastrophe Conferences. And, people like Sagan and Alvarez and Gene Shoemaker and others who were naysayers, I forget that Professor Princeton was one, but whatever, they would stand up and have arguments in front of people that were then going to present papers about the more nitty gritty of how do you tell this versus that. And
do those kinds of conferences still exist?
Well, the Grand Catastrophe Conferences of the late 80s, I think it was 86 and 89, might have been 86 and 88, were funded by a consortia, I think it was NASA, NSF, a few others. It brought together people right at the time that people were worrying about nuclear winters and, cosmic collisions. And now we have this Chicxulub event, then not even called Chicxulub, it was called the KT, for lack of any better name. And, I went to one and presented data for the impact event in Kazakhstan that I visited, called Zhamanshin, which actually means bad place, apparently in Kazakh. But, not of the consequences of that. So I don't think they have them as formally organized. They're more as part of subtopical conferences. I haven't been to one since we presented at one in Canada in like the early 90s up in Sudbury. But
yeah, there's this feeling that I kind of mentioned this at the beginning, where it's like there was a period of time in the 60s and 70s where it was more playful, like where you could organize that kind of conference and it wasn't part of 10,000 people showing up. It was something that was smaller and yet and maybe because of its size was able to be so
impactful.
Not even impactful, but just crazy. Like the idea of scientists getting together now and mulling over some kind of massive paradigm shift event where they're really on opposite sides of it almost feels like something that you could only read about in a history book. And I wonder if it's possible to shift that, because I feel like I really struggled with this during grad school, because on one hand, I recognize that the systems that we have in place right now, which are, pretty strict funding rules. In biology, everybody's focused on, cancer treatments and these like big questions of how are we going to develop the technology. And so that sort of funding structure has opened the doors of science to people who would have never had access to it beforehand, right? Because there's good funding structures. People are interested in bringing people in that are not generational scientists, that are from different backgrounds, that are from different levels of expertise. And it's like, that's on balance, that's a really, really good thing. And so I don't want to do away with that, but I wonder how to bring that magic back of like the Thomas Gold style just missives, because it doesn't seem like it's productive in the way that we expect our science to be productive today.
Well, I think what you're saying is the narrative style of science that came out of the 19th century. I mean, Darwin's writings had expressed that is sort of been taken away by rapid publication of a very important, detailed, heavily documented point, not the whole story of developing that thought process. I mean, there are review papers that do, I think, what you're saying, where people review. At NASA, we have something called these this institute that's now distributed for astrobiology, the study of possible life that doesn't follow Earth rules. And some of the nodes that are competed every 3 to 5 years really are rather creative. One, is a laboratory for agnostic biosignatures, meaning look away from your Earth biases, think differently. A young woman runs that, Sarah Johnson at Georgetown, with a consortium of people, and good person to talk to. And their idea is to not look at what we think it ought to be, but let's see what disturbances and what we could measure might tell us it can't be, physics and chemistry, geology. It's got to be something else. What disequilibrium signature could we detect that we didn't even know was there? The same way, people started looking for, viral transport in the stratosphere, and especially during COVID, of course, became interesting. But anyway, though, so I think that style, it's gone out of vogue because, people don't want a 50-page monograph or, whatever, telling the story of how they discovered, the toad bug. That was a joke. I was interested in the toad bug as a high school kid, but little tiny thing that hops around on pond scum. But anyway, that narrative is not as important as other things. But I wanted to just say there are perturbations that do allow what you're saying to happen. For example, you folks and I are living in the web era, and that's not the World Wide Web. It's the era of a telescope that's so good that it will change how we see our universe, and that's the James Webb Space Telescope. And literally in a year of first starting operations, the stuff people are seeing that are starting to wonder about is beyond beauty. It's just, whoa, we didn't know that. Could that be this? I mean, could we actually see this? And once you make a paradigm leap, you get off the track. I mean, it's a disequilibrium. It's that punctuated equilibrium thing that Gould talked about in life stories that happens in physics. We can now measure the spectroscopic properties of atmospheres around exoplanets. I mean, come on. That was, if you hand wave, back in the 80s by a few brilliant women and men who said, well, we can be good. But now we're doing it. And, those kind of things, they don't happen instantly. Sometimes they take 20 years to build. Sometimes they happen organically by people talking, like you said. And so I think that's where innovation in science with more connectivity will pick up what you were saying, Shiloh, which is that we'll find new ways to connect. And some will be on the edge, and maybe not fully measurable, not testable as well as we'd like, and others, will be different. And in biology especially, which is a big frontier, not as well thought about in time as of course, some of the great paradigms in physics, is an opportunity space, I think. I mean, I'm not a biologist, but I see it. I just, don't understand it, quite frankly.
Well, did you see this Scientific American article that just came out about the James Webb by any chance? I just saw it this morning, but it was kind of interesting because they had this attitude that was kind of like, are we actually ready to change our minds about this stuff?
Right.
Which is interesting because in all of these giant leaps in our understanding of nature and of the universe, it seems like there's sometimes it takes a lifetime of building up all of this evidence for somebody to be able to come along in that cultural landscape and say, guys, we need to look at this completely differently. And so I don't know. I'm very optimistic because I've seen huge paradigm shifts before. I just wonder how soon people will be ready to look at all of that extraordinary and somewhat contradictory evidence that's coming out and really, really look at it from a different angle.
I think it's happening. Honest to gosh.
Me too.
I think happening, some of the younger folks that aren't as biased by 50 years of a paradigm, who are willing to say, well, but what if it's this? And, and that will drive different observational frameworks. And, we have a period of years to use this thing before we build the next big one, which will take another, and that's in planning, which is great. But these are opportunities. I mean, I think a colleague of mine who used to be head of science for NASA once said, if we were in the year 9999 and we look back to now, early 21st century, what would we know? Would it be Beyonce? Would it be, what big thing would we be talking about? And it might be that we finally crawled out and started to see the bigger picture. And it were those first couple of space telescopes and a few other things, of course in biology too, which is not my area, but that we started to recognize what we didn't know. And we started to take the risks of figuring out, what do we need to know? I mean, one of the reasons why I'm interested in Venus, because we have a sister next door that's less well explored than Pluto. So because of an engineering boundary condition problem, she's not the most convenient to go to. So, no U.S. mission's been back to the atmosphere of Venus since 1978. My God, that's, what were people doing in 1978? I mean, there were no iPhones, trust me. And,
well, she's so similar and so different from us, right? It boggles the mind, right? All of this geological activity, no magnetic field, like what is going on? She's very perplexing. And of course, everybody all throughout time for tens of thousands of years has been obsessed with Venus.
Well, yeah, and the fact that she's so different in the same neck of the woods with a story that's probably lurking in her big atmosphere, which is an ocean of air. Near the surface, it's actually only 10 times less dense than water. Really, how do you handle supercritical CO2? They do in manufacturing, but that's about it. We don't live with it. But that's the Venus of today. But it wasn't always like that. Some of us think a billion years ago or less, there could have been surface ocean waters, and it may have had mountain building more like the tectonics we know and love with our terrestrial model, but we don't know. And so the next foray of missions, commercial plus by space agencies, are going to tell us stuff. And all the kids, young folks like you and younger, are going to wake up to a new Venus. And we'll say, she may be a little harder to work at, but, let's face it, Mars is great because it's also fantastically interesting, but it's also really convenient. Electronics love being at minus 20, trundling around. It's great. You're not worried about too much. It's super. When you're at 450 C and in a caustic environment and, you have battery power for a couple hours if you're lucky, or some other power source that would require more creative things, you got to get a lot of work done fast or figure out a way to handle it. And so I see these scientific exploration challenges, the ones you were talking about, why aren't we edgier, as catalysts for the engineering to come out of their socks and solve the problem for us. To me, that's the beauty of it. Science is great. We ask the questions, we want to know stuff, but engineering solutions that let us make the progress on it. It's that partnership that crosses the boundaries and let us do things. And that, whether it be astrophysics, biology, nanoscale, everything, those are those frontiers. I like to say space is a forever frontier because, it is basically counting across how we look at dimensions. And I'll let the physicists describe all their great, multi-dimensional stuff, but it really is. But so is the nanospace that builds, the rigging to get to life and atomic, basic atoms and all that stuff. And so at both ends of the scale spectrum, we have these magical forever frontiers awaiting us to use and understand and learn from. And, we've just opened our eyes to them. It's like, what a great time. Seriously, it's marvelous.
I think that what I see here is that before you bound science by engineering, what you have is mythology almost. You have stories that you tell about what might be, and there's these massive actors, and it is theoretical and fanciful, and you have to be bordered, in order for it to be, utilitarian, you have to be bordered by what's possible in terms of, some fundamental axioms that you take to be the rules by which objects interact. But then when you take engineering is the time where everything is on the line because you suddenly can confirm or deny the mystical that you have proposed in generations before. And so when you go to Venus, for the first time since 1978, what are the things that are on the table for confirmation or for denial?
Well, we bring the tools of the trade. It's almost Sherlock Holmesian, in a sense that we have a problem and there are clues. We have a giant atmosphere staring at us. We can't even see through it without windows in the infrared. And so we're challenged by that. We have to be in the atmosphere. We have to sample the atmosphere. In the case of our mission to Venus, called DAVINCI, named, quite frankly, for Leonardo, but also an acronym. Have to have acronyms at NASA. But it's convenient that Leonardo gave us his name for an acronym. But our trick is to bring the labs that we have and that we use for samples from the moon and in biology, bring the labs with us to the problem. That's an engineering solution. So we make a spacecraft, it's basically like a submarine, that intakes gas and measures it at the scale we need to understand what made it, how did it get that way. We look at certain things like noble gases, which the way they fractionate tell us the history of things because they don't react. So the ratios of their isotopes are, they're fossil records of what happened to a planetary atmosphere. Was it reaccreted? Was it blown off? Was it made by volcanoes? Was it cometary? Was it cycled? Blah, blah, blah. Those tools are at our fingertips now. And we have them in the labs. Kids have them in school. We took them to Mars on 2 rovers. Blah, blah, blah. We have them on the space station with, crew, women and men working with them. Now we bring them to Venus in a robotic craft. And so to get to your question, we ask the questions of what could have been. And I think there is mythology and there's also visioneering. I know it sounds like a Disney term. It may have been started there. I will leave that to you to tell me. I heard it. And, Thomas Edison was once quoted as saying, vision's great, but without implementation, it's a dream or something like that. I mean, that's an approximation. So we visioneer what we think could have been a story for another world, like Venus. Maybe she despun and got into this weird motion that changed the way she behaved relative to Earth. Maybe she lost her oceans to the atmosphere and hydrogen was lost to space. And we have this strange planet that lost its habitability. Maybe she did something else different that we never even thought about. So we need to make the measurements that open our eyes to the possibilities because we don't even know all the possibilities. And that's what's cool. I mean, we're going to be going with DAVINCI, coming down and imaging over a 10,000-foot mountain range that some people think are the continents of Venus, which would be cool because we have continents on Earth. That's a story of old rocks. Really cool. God love them. Or a story of something new or something different because those mountains don't look like those to the things we've seen that we're so used to on Earth. And so why? Why did Venus work differently?
How are they different?
They have textures and patterns and things when seen by the radars we've used to see them that just don't look like the kind of things we have on Earth. There are some places on Earth that are analogies. The ancient mountains of the Pilbara of Western Australia, quasi-similar. The young collisional mountains of the Zagros of southern Iran, maybe. There are places that have resemblances statistically, but these are different. They're taller. They're distributed differently. Why is this jigsaw puzzle of Venus, not assembled in front of our eyes the way we've come to see our own history on Earth? We're starting to use for the moon, which is a great place to test. And, for me, I like the what if it was really good. I call that finding the pony story. You think you probably get where I'm going. So, you put a kid in a room with a bunch of stuff they don't particularly want, and they look for the pony. So I'm looking for the pony on Venus. I want it to give us the clues to tell us Venus had oceans, and it lost them. Why did it lose them? What does that speak to planets that are at the edge of a habitable zone relative to a parent sun, as we look at dozens of other ones with James Webb and with future telescopes, Nancy Grace Roman, the big HWO that's being conceptualized now, when we'll be able to see things, much better. I mean, you young folks are going to see the glimmers of light directly from exoplanets in your lifetime.
Which has really changed the way we think about our own planet, too. It's been incredible. And our solar system, right? We used to think all solar systems more or less probably look like this, and it turns out we're like the complete freak in the bunch, right?
We probably are. And that's what is big rocky planets, some atmosphere, some not, blah, 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 clustered, habitable zone, not, oceans under planetary crusts. The search for ocean worlds doesn't mean they have to look like Earth. And that's a beautiful story. Maybe they never looked like Earth and they lost them. And these are stories.
Or maybe they will later.
Yeah, and that's just true. Most of us suspect oceans of briny water under the crusts of Europa, possibly Enceladus, maybe Ganymede. It's just the possibilities it's beyond the mythology. It's the visioneering of what could be if we only knew more. And, that's what I think.
There's something interesting about the James Webb, which is that it's pushing our sense of how quickly things happen as constrained by the age of the universe. Where you see all of these galaxies that are fully formed at redshift, 10, 15, 19. And I wonder if there's a sense that it's possible for the timelines to shift. Where I feel like even...
And how that will impact all of our timelines for the production of other bodies.
Yeah, because we've had a lot of conversations with people that do radiometric dating. Like there's this guy, Chris Kirkland, at Curtin University in Australia, who they put together a really interesting impact theory on the basis of solar system transit through the arms of the galaxy.
Mm-hmm.
And so we talked to him, and one of the things that we kind of came to is that the 4.5 billion year time limit on Earth has to do with the limits of melting. And so what it really tells you is that's the last time that everything was molten, and that's the time that we pin to being the age of the Earth. And I've always wondered where if there was a sufficiently high period of impacts that melted the entire Earth. And so what we're seeing is a readout for the age of the last sort of universal melting. Is it possible that we'll push the timelines as our timelines for the entire universe start to change?
Well, that's a big question. But to the point of Earth, some scientists believe the best chronometer for the birth of Earth as an accreted body that was starting to behave as a planet was more like 4.67. And that's based on the earliest possible extrapolation of those radiometric clocks for rocks from the moon and for meteorites. And just saying, well, this is one solar system. A lot of crap happened at one time to get it organized. And that had to have happened pretty quickly based on the models of the condensation and accretion. Because if it took too long, things would have broken up and there would be more little stuff. So, and those are models, not fully constrained. That's why we want sample return, all that good stuff. So for Earth, of course, where you're going is that we may have had cycles of a global crustal magma ocean that then froze out, that is congealed, to freeze in these records in these clocks that we use, these radiometric signatures, many different ones, some really exotic, I love them all, but they give us different time resolution, as you know. Rubidium strontium is a big one in certain rocks that don't leak. In the younger rocks, we can use argon 3940 and use potassium. So these clocks have limits. And so you're right. We don't really know, but when we run the clocks on the rocks we have that give us, plateaus, we can come up with a time. So do we know if there were cycles of these things? People are questioning this idea of late heavy bombardment, a whole cluster of impact that happened in the first few 100 million years of planetary formation, accretion, crustal, establishment, and then it terminated. And, Graham Ryder and others came up with that based on great data back in the 70s and 80s. And now people are starting to say, well, hold it, what if it was a leap year transition as the debris left over from planetary formation, was captured and collided with, and then, didn't spawn a lot of other stuff. We don't know. And that's why we need to look at these problems in different ways. And so the chemistry tools of the lab now are so much better. We can look at different clocks. We can look at other isotopic ratios to see how we might be able to limit and constrain. And a lot of those things are just happening now as people get more creative with the tools at hand. I mean, we can measure, nanomoles of things now, if not picomoles. So you can start to see the potential of the measurements. We can use non-destructive imaging to decide where we're going to make a sample to then do, nanoscale sampling with TEM or whatever people use. So I think you're right. We don't know. So we can take an idea, the last crystallization time frame when things went from melt to solid, and say that's the age, but it's probably a conservative one, and there's probably other horizons. Now, how that applies beyond planet formation, silicate planets with, crusts and things, is another very interesting But whoa, big problem, because all those timelines, they have to be looked at in the context of the scales in which you're looking at in the energy spaces. And, again, remember, most of the universe, we don't even see any, with dark matter and dark energy aspects, we're barely seeing, the forest for the trees in many cases. So that's where we need these astrophysical observatories to build the boundary conditions for the models that the great thinkers can then turn the knobs and think. And I think that's going to happen. I mean, it always happens, but sometimes it happens in spurts. And, I think we're in one of those spurts now, and there's a lot of bright young people who can read a lot of stuff and use new computational tools to do the kind of work that, 30 years ago, we would have said, no way. I mean, we won't be able to even measure that. When I first suggested we map Mars, and a bunch of us, there's a small number of us, with laser altimeters in spacecraft, timing the speed of light to a nanosecond to measure the height of the ground, to something like this. Let's just say I was met with some skepticism by my peers. Many basically laughed me off the stage. I said, but the engineers know how to do it. It's physics, timing, electronics, and we know how to gate it and blah, blah, blah. People didn't believe it. The engineers delivered it. We've mapped the planets that way now. So, you have to sometimes be tenacious against the pushback of people that say, why don't we just do it this way? And that's the approach we're taking with Venus, bringing a camera that can see through the murky, carbon dioxide atmosphere from below the clouds to see the surface and actually measure what it's made of. I mean, no one would have dared do that 10, 15 years ago. And yet now we think we'll do a good job with that for the community. And, that's one trick of getting around the problem of having a 20, 25 kilometer cloud deck that's largely, occulting of what we would normally see if we didn't have the big atmosphere. And we see that kind of stuff on Mars. So these problems become demytholized and demystified in the terms of your show by bringing creative ideas and new people to the problem with opportunities to innovate at measurement scales and modeling scales and computational scales. And you put those together and, in biology, with metagenomics, we don't have to culture everything to see what's living. Wow. I mean, come on, that's like revolutionary. And I can just imagine what's coming next. And, you'll tell me, I'm sure, but whatever.
What does your day-to-day look like?
Mine, well, right now it's driven by a lot of stuff that is the necessary evil to getting missions that go to new places. So we competed across 2.5 years to win a chance to fly to Venus with DAVINCI. I mean, our final proposal was 1,600 pages of detailed stuff and another 10,000 line spreadsheets of, everything. So not for the faint of heart. Thankfully, I wasn't doing the spreadsheets, as we say. And so, but my day-to-day, and I have two deputy PIs on DAVINCI who are both brilliant young women. So we have a team on this, is to basically do the paperwork that produces the contract with NASA, who gives us the money to do the mission. And the first step after selection is to make that arrangement that we are going to deliver these things. These are the questions, here's the precision, and that contract is our, that's our metric, like the report card you have to grade against, in school. And those are very important pieces of paperwork. And then we derive a level deeper what we think we need to do that. And then we do that deeper down into the levels of engineering where we finally get to, we need this much fuel to fly to Venus and go around it a few times to get to the right place. And it works out. And over the first couple of years of the mission, that's the paperwork, the documents that shows you'll be able to do it for the money that we're cost capped to have. Because we don't want to lie to people and say we can't do it. We have proposed to do it with a schedule and a cost. And we take that extraordinarily seriously. And sometimes that doesn't work out. But in our case, we're going to die trying because that's the contract we have with the taxpayer, really. So for me, we're worrying about that while we're also engaging our scientists and our engineers to polish this design, which was proposed with lots of detail. But once you start building it, buying the parts, looking at lead times, you realize you need a little more or a little less or something a little different. You can't get that part. And so we have a team. In the end, it'll be a couple thousand women and men who will work on this across the U.S. to build this mission to Venus for us. And so, it's great. And, we hope to see lots of young people engaged as part of our program at all different levels to take part in this mission, which we think will be pretty epic. But my day-to-day is worrying about all those things and still doing science. We have recently made a new map of the mountain region we're going to by taking all the Arecibo radio telescope data from Puerto Rico and putting it together, computationally deriving slopes, and then correcting them for what our mission in the 90s did in Magellan, and making a new, much finer scale map of where we're going without even having to fly a new mission. And that will help guide us into what to expect that we will see as we come out of the clouds and see this kind of terrain on Venus known as tesserae that has not been seen on any other planet. And so today, of course, we haven't seen every object. So for me, it's extremely exciting, and it's an incredible opportunity. But meanwhile, I'm also doing science, studying Hunga Tonga Hunga Pai in Tonga, because that was an incredible eruption and the record of the youngest impacts on Earth that might have been consequential to history of our planet. I'm kind of one of those curiosity-driven folks that can't help myself.
I want to talk about the Tonga question, but before we get there, I wonder, you said something about the engineering difficulty of getting to Venus.
Yeah, because the first probe the last probes only lasted half an hour or something, right?
But it sounded like it was more than just the corrosive atmosphere. It was also about, because somebody else that we talked to mentioned that going inwards in the solar system is much more difficult than going outward. So is that what you were referring to, or were you referring to the atmospheric conditions?
It's basically everything. Okay. So our job with DAVINCI is with a dining room table-sized carrier spacecraft with big 6-foot antennas on it, carrying a 600-pound, basically it's a 3.5-foot mini submarine made of titanium with a bunch of inlets and eyeballs and antennae, is to fly around Venus a couple of times, collect data. We have a new instrument on our spacecraft that will actually use AIML techniques to try to measure the chemistry of the clouds without sending every bit back, because it will generate a ton of spectra. Because there are magical things about the Venus upper clouds that have terminology like mystery absorbers, and it sounds like it's out of Sir Conan Doyle's books. What's a mystery absorber? Well, we don't know what it is, so we call it a mystery.
Dark absorber.
Yeah. Yes, they're coming for us. But that was a joke. But anyway, so we actually fly around Venus, around the sun twice, to set up for our entry with our probe, which hits the upper atmosphere like a capsule coming back with the crew from Orion, and has to shed all that heat, pop out with a big parachute, basically fall through the atmosphere slow enough to collect the samples we need to make these extremely precise parts per million to parts per billion measurements without getting clogged or any of that. And then when we get below the clouds, cut the parachute and free fall, kind of like a heavy rock, in this thick atmosphere while we're collecting hundreds, if not thousands, of more measurements and imaging all the way down. So the problem is going in toward the sun, but going to the right place. Venus is a big planet. It cranks around very slowly. A day is longer than a year on Venus because of its rotation. So we want to hit this mountain range. It's about twice the size of Texas, half the size of Australia, if you prefer that, metric. We want to hit that and descend all the way through that atmosphere during a period of an hour of primary science, and then whatever we get once we hit the surface. And so we have to do kind of like the scale of science that the Curiosity rover is doing on Mars in kind of like a drive-by mode, moving at 20 miles an hour, not the pace I would walk with my dog. So we have to do all that, given that there were many interesting challenges that the US and Soviet probes discovered about Venus. Inlets being clogged by big, thick aerosols made of hydrosulfuric acid and others. Other things like that. We can't have that happen because we want to measure the gradients of chemistry through the atmosphere as it changes from being a rarefied, not too bad place to be, pressures and temperatures kind of like those on a hot day on Earth, to hellishly unimaginable temperatures like we see now near the surface. So we have to have our instruments, which don't want to see 450 degrees centigrade, operate as if they're in a nice lab environment. And, the students are running them and we're all doing our work. And so it's a containment problem. How do we bring the stuff in, get rid of the exhaust gas, bring in the images, compress them, scan them up at up to a megabit a second to get them off the spacecraft to our flyby carrier spacecraft, which will be listening, do all that in a syncopation, kind of like a ballet dance, and return that data. And then our spacecraft goes on around the sun. So, it's a choreography really that has to work. We did it at Titan with Huygens back in 2004. It was done back in the 70s, not trying to make measurements at the scale we're making. People made 2 or 3. We're trying to make thousands. We'll make a measurement of the pressure and temperature and winds every 50 feet throughout the entire atmosphere. The kind of thing you do for meteorology on Earth, we're going to do that for Venus. So all these things together in one mission that we had to openly compete to win the possibility of even doing it, it's a lot of stuff. So it's an engineering marvel that we can make all that work. We even have an adjustable data rate where our, if you will, submarine, it's a probe that's roughly like a big sphere. It communicates and dials up and down its data rate based on the signal strength with the mothership, which we call CRIS, the Carrier Relay Imaging Spacecraft. And so that'll allow us to get more stuff. We have to name things. Otherwise, they have weird names that, And eventually, by the way, we'll have a naming competition, we hope, for our probe spacecraft, so young girls and boys can, win the chance to name her. But that will be when we're closer to launch. So all this is the engineering of having to do a mission like this. And no one's done one anywhere near like we're trying to do since the Soviet Vega probes of 1985. So, which were great. And so our job is to make best use of the worst case fall through that atmosphere to understand an entire world with this atmosphere that is so much bigger than Earth's, it's like an ocean. And in it are the clues of why it's that way, chemically, physically, and in the rocks on the ground. So, our discovery potential is enormous. We don't even have the vision to know what we might discover, but we know what we're looking for to measure. And if Venus cooperates, we could see, a world that lost its oceans with habitability. We could see a world that never had oceans, but a big steamy atmosphere for a long time. All those things are within the realm of what we could measure to demonstrate. And then all the big climate modelers will turn their dials and dial in the real Venus and ask questions about how does she relate to the real Earth that we know as we live here.
Yeah, I'm curious about the more nerdy aspects of what we know about Venus too. Is volcanism on Venus compositionally different from volcanism on Earth? Is there the same level of water content? Because I know that the Earth volcanoes are very watery, actually. And I wonder if there's no water over there. Is there water?
Well, first, there is water vapor in the atmosphere. And so if you condensed all that out, it would be appreciable, not, like Earth. Secondly, the role of water and other volatiles is really important in how liquid silicates operate. And literally, you could take a lava rock that erupted in the Azores Islands and melt it and add water to it in different ways and make the rock totally different. So on Earth, we have the most simple rock in the solar system. We all dearly love them, called a basalt. It's about 3 minerals, maybe 4 if you're lucky, and there she is. And so the crust of the Earth, the ocean floor, the mare of the moon, the plains of Mars, they're all made of that. Soviet landers measured what, to first order, look like basaltic kind of rocks. They're rich in iron and magnesium, they're low in silica, and they're easy to make. Mother Nature does a great job with basalt, and they make volcanoes. So all that is logically what to expect for Venus for the very dominant plains of the planet. And 80% of the Venus planet are rolling plains. They're kind of like the ocean floor of Venus, but we don't know that there were oceans. We suspect maybe. So the problem is, as you just said, if you stick water into the liquid stuff, it can change the composition from those nice basalts that ooze lavas like Hawaii and Iceland. It's all exciting, but great, to things that look different. They can have compositions like granite. And if you've ever seen the weirdo rocks of some parts of Iceland, right next to a lava that is black and looks like charcoal, are these pinkish, funky rocks. What is that? Well, that's mixed magnetism. Same thing happens on the island of San Tomé off the coast of Africa, where you have these big spires sticking up with all these vegetated lavas all around. And basically on Earth, sometimes water leaks into the system and crazy stuff happens. That's what happened at Tonga Tonga Honga Pai when the Pacific Ocean entered the magma chamber, when the caldera collapsed last January 22. And, you stick a ton of water on rock that's, 1200 degrees centigrade. The water is 20 centigrade. And you can imagine the kind of fuel coolant interaction that occurred. In other words, it blew up and produced, a big eruption cloud, blah, blah, blah. So on Venus, if there's water in the system and it was oceanic and crustal, we could have the processes of growing different kind of volcanoes, the kind that explode, the kind that make different kind of mountains, the kind that, people have studied, that it could produce calderas like Yellowstone, Topo, others like that, where there's a big explosive phase. The problem is when you look at the plains, and a paper just came out from WashU with Paul Byrne and his student, they've cataloged, thousands of volcanoes on Venus. And most of them, shape-wise, at moderate resolution, look like what you'd expect from basaltic volcanism. But we don't know. So one of our jobs with DAVINCI, coming out of the clouds, will be measuring with images the near-infrared bunch of different bands to tell us what the ground might be made of. Could it have evolved beyond these really dark, iron-rich basalts? Could it be something different? Is it erosional mountain ranges, like the old stubs of the mountains in North America, in Europe, or is it different? And if we can tell that at scales under the clouds, which will be, like a Landsat picture of Earth, that would be great, because above the clouds, you can't do that. Your whole resolution is perturbed by looking through this giant cloud bank. So anyway, we don't know the role of water in the history of Venus in volcanism. Do we suspect Venus is volcanically active? Of course we do. And a recent paper just came out by Herrick and Hensley that shows what all of us have been waiting for years to see, that things did change during the Magellan mission. And, I think we'll find more of that. And whether it's big change or a collapse when a volcano oozed a little lava remains to be seen, but that's very likely on a planet that's as big and hot inside as Venus, which is what Earth does. Hard to imagine she is not doing that. So I think, in fact, as Earth has to release that heat, and we do it in the ocean ridges, under the water, it's all great, under the oceans. On Venus, if that's happening or happened in the past and has been slowed down because of the thickened crust, all these are possibilities. But the role of water is critical.
It seems like there's been a lot of really interesting reports about the geological presence of water too, and like the hydrated ringwoodite and these, I don't know how speculative they are, but the idea that there could be oceans worth of water in the form of hydrated hydrates, let's say.
Magnesium hydrates, yeah.
And if that's playing into the course of volcanism on Earth, it would be maybe a point at which the two planets could differ, because there's other really bizarre things. Like if there's all this volcanism on Venus, there must be tons of convection, right? But we don't see the same plate tectonics that we do on Earth, which is very strange.
That's true. And some colleagues think that Venus had its mobile lid tectonics, as it's called, more terrestrial-like, but perhaps not with as intense subduction, because it, had a different state of convection and an organization pattern. And then once the lubricants associated with that, water and sediments that were dragged down, disappeared, Venus went into a different state. Earth has stayed in the state it's been in for a long time. We don't even know when the onset of that state was on Earth. So studying Venus through the lens of geodynamics and geophysics, with the scale of things that we've done for Earth and now for Mars, would be incredibly important. And that's why two of the missions that will be flying in the early 30s will be looking at those signatures using topography and gravity, using radar techniques to try to integrate that the way we have, for Earth and Mars. And so that's a big question. What could we learn? And on Earth, wet sediments being subducted drives all kinds of exciting volcanism and produces many things we know and love. But that's different than continental cores and those cratons of Canada and South Africa and Siberia, which were formed in a different way. So there's a time history on Earth. How does that apply to Venus? We need to piece together the puzzle pieces to try to figure that out. And I would be very surprised, just, visioneering here, if the role of water on Venus wasn't critical, as it has been, of course, on Earth and Mars to some extent. And some scientists think the mountainscapes were shaped by erosion in hydrologic processes. And that's one of the things that our mission will test, because our final imaging resolution will be, meter scale as we come in, and if not finer, if we get the data back. But anyway, you're right. Water driving the kind of compositions that become involved in the igneous evolution of a planet and its crust are critical. I will say this: the landing sites that were best measured by the Soviets, and I worked on that data with them for my thesis, the Venera 13 and 14 sites in the rolling plains, certainly looked basaltic, with either extremely thin little lava flows or some kind of volcanoclastic sediments made by those kind of eruptions. I mean, those are the most logical possibilities for those things, and they probably cover large areas. We only saw 100 meters of local real estate with the imaging that were done by those magical landers. But they didn't do descent imaging. They landed and then took panoramas. So, I just think there's so many possibilities for Venus, just like we're going to have a totally new Europa once we get the Clipper mission out there to see how she works, just like the mission Mars Reconnaissance Orbiter at Mars, that several people said, we don't need it, let's just go land. Well, it's shown us a new Mars. And, 15 years later, it's easy to say that, but it was a tough battle to get that mission, through the gauntlet to fly it. And I'm still extremely proud of it, because it opened the recon to tell us how to go and where to go, and allowed Curiosity and Perseverance to pick their spots really well. And that's been really important. And on Venus, there's so many good spots to go. I mean, we're going to hit something really big, that, 30s and 40s and beyond, the surface vehicles that we can engineer to do that. I mean, they'll have so many cool places to go. I mean, Venus really has incredible real estate. It's just hard to imagine through the eyes of radars, because we're not there seeing it, the way a rover crawls up and sees mountains in the back. It's, it's a different vista. It's less human personal in some sense. But we want to change that.
Go ahead.
Go ahead.
Well, I was going to say, so I saw a paper, I think it was the recent paper, where there was a map of all the volcanoes on Venus, and it was kind of stunning, the sheer number of them. And from what I understand, Mercury is pretty inert relative to Venus. And I wonder if you have sort of a mental model for what accounts for their differences.
Well, I have not worked with Mercury, so I will just say the Messenger mission and the Bepi Colombo one now that are working at it are going to change everything they already have. Sean Solomon's team on Messenger was staggeringly good and came up with a bunch of new paradigms. Mercury suffers from, the problem of size. She's a small planet. And, you can only do so much convection or transfer heat, whatever way you do, because it's a volume-driven kind of process. So Venus is essentially the size of the Earth. And so she's got a lot of volume to play with. And so even in a despun state, which is constantly, by the way, caused many great theories by people like Tom Ahrens and others to wonder what that does to the geodynamics of a planet, which is not, rotating like Earth and Mars. But take that aside, certainly has an impact on the internal dynamo that a magnetic field would require. But I think size matters. And so the Venus potential and actually the mapping from Magellan, which has been extraordinarily good, shows that distribution of volcanoes that Paul Byrne and his student published with 85,000 sites down to scales of, a kilometer or so. I mean, I was struck in a paper I wrote in 1990 by these little tiny Icelandic-like shield volcanoes we could see in the very murky data from the Soviet Venera 1516, and wrote a paper and said, well, if there were a lot of those, there could be a lot of Icelandic provinces on Venus. But that was before Magellan. And now Magellan's allowed Paul and his grad student to do an incredible job mapping Venus. And so you take all those volcanoes and you just integrate over time, because their expression will change as they're buried by other volcanoes. And it just says, my God, this planet's erupting. And that's one of the signatures that all the missions going to Venus are going to look at. We're going to look at helium isotopes and other things with DAVINCI to see if we can tease out the chemical signature of those processes. Others will use the geodynamic signature with interferometric SAR. And putting those pieces together, we'll have a better view of what's happening. And
You
I
said
think
something about the magnetic field production having to do with the rotational dynamics. Is that correct? Because it's interesting because Mercury has even a little appreciable magnetic field, and it doesn't have all that convection, I guess. What's going on with Venus's magnetic field?
that's a good question. And there were measurements made as part of the Pioneer Venus program of a very small scale field, I'll call it, and there's an induced field from solar wind interactions, of course. But in a slow spinner, a lot of different dynamics, and the magnetohydrodynamics, which is not my field, but colleagues I know that work in it, have been pondering that going back, to the 80s. So why didn't she have one? Did she derotate? And could that have been possible with giant impacts? Some people looked at that. Not too conclusive, but
because she's spinning the wrong direction too, right? She's the only one that's spinning the opposite of the rest of us. It's very, very weird.
Very strange, and yet she has a super rotating cloud deck. And once you get down to the surface, best we can tell, the winds are a meter a second. That's 2 miles an hour. So from the data points we have, but
that's more like a water wave at that point, I would assume.
Well, it is. It's like a density current that would come off a volcano, underwater, which we of course see. Those wiped out all the fiber optic cables, by the way, in Southwest Pacific last year, which was very interesting. But yeah. So these enigmas, these, conundrums about Venus, I mean, right now, the best we can do is come up with a model and say, well, if we had this, we could do that. But that's why, eventually the community of people interested in our solar system and beyond need to measure Venus. To me, Venus is a perfect ground truth for the exoplanets that we know we can measure. Venus would be a good target around a smaller star than ours, because we would be able to pick it out of the murk with telescopes like James Webb and do transiting exoplanetary spectroscopy. She's big and hot and has an atmosphere that's distinctive. A Venus in a more Earth-like state may not be as distinctive, but we may still be able to see her. Earths are hard to see, as you know, and we'll need bigger telescopes with more aperture and other tricks to see them and to occult out the parent stars. But we'll figure that out. I mean, I think the community has great thought designs for that kind of thing. But for our Venus, we actually have to know what the real one is to use her to understand those exovenuses that many of the people in our DAVINCI team are going to be looking for and are looking for with Webb and others. So, and I think we'll find them. They actually, according to Stephen Kane at UC Riverside, they're probably going to be the more common and detectable than many of the other kinds of silicate rocky planets that we know and love. So that'd be cool. So
are folks is there any interest in people going out there? I read about this proposal for essentially floating a station at the top of the atmosphere. You could have something, I guess, that would be in orbit, and you would avoid all of the heat problems if you spent some time in the dark. And I guess it's somewhere close to atmospheric pressure at the top, an Earth atmosphere that you could just camp out on.
Well, there have been studies, very good point. There have been studies by some of these funding opportunities like NIAC, which are, NASA Institute of Advanced Concepts, to look at floating observatories that could handle sort of the mid-cloud, where it's about 1 bar of pressure, temperatures, 20, 30 C. Or a little colder. And you could literally produce an airship that would fly there. And there could be great science. Of course, getting it there and inflating it there, it's not quite that trivial because it would have to be big and be moving around fast, but it would produce exquisite observations. Others have thought about the idea of lots of little flying kite-like things that would be deployed as, a swarm into the atmosphere, and eventually they'll hit the deep hot part and not do so well. And so all these great innovations are being looked at by smarter people than I as next steps. And, there's even long-lived landers that don't produce a lot of data, but that can survive with heartbeat type kind of measurements of state variables at Venus, at a few bits per second, not the scale you'd need to transmit a complex chemical spectrum or image. So I think engineering, as it's done in the deep sea, we're part of, we're in the midst of the Seabed 2030 project to map every inch of the ocean and have it as an integrated data set for all of us for Earth. As that is doing so well, for Earth. I think, the putting Venus into focus with 21st century tools and all the great minds of a whole new generation of people that aren't biased by what people tried in the 70s and 80s is fantastic. I mean, that's the cycle time. Now, I think it's one last little historical note. It's interesting if you look at the history of exploration, that there is this statistical commonality of sort of a 50-year, 55-year gap. So between Magellan's circumnavigation, and I know Elcano came back, but that trip, and Drake's next circumnavigation, as recorded in history, was about 55 years. And the time it's taken us to look at returning humans, at least to lunar orbit, you saw with Artemis, with the crew, and this great group of women and men going, it's going to be about that too. And that cycle time seems to be scale of change and recycling through people to come up with new solutions to problems of consequence. And I don't know whether it's random or it's the way the cycles of investment, history, engineering, and exploration happen. But it's just an interesting observation to me.
There's also an aspect of human lifetimes here, right? Where it's, you have a generation that goes and they learn what they can, and then they get occupied with other problems, and then the next generation grows up and starts to think about the same place, and they're like, well, maybe they missed something, maybe they didn't see something, maybe there's more that we can get from it. And I don't know if this was always the case, but I have this feeling sometimes where I look at data that's collected 50 years ago, and I look at the data that's being collected for perhaps the same questions now, and it's kind of astonishing how different the results are. And so maybe that's just the amount of time that it takes for an imaginative mind to come back to the same question.
Well, I think that is a big part of it. Another part of it is, when we realized weren't able to make the kind of conclusions and outcomes that we thought, say, measurements made 50 years ago, because of whatever limitation, sampling, data rate, whatever, we go back with things that are often 10 to 100 times better. And, think of looking across your house at a scale that our eyes see, and then doing it 100 times better with a giant telephoto lens. I mean, you'd see different stuff. And so sometimes you need both. You need the recon phase to ask the question and say, well, we didn't see, we expected that. Now we dial in with the next phase with new people without certain biases, and they build on the legacy of what went before. And, I think that's where Venus is. We're ready for that next bold leap. And likewise in areas on Earth, the deep ocean is certainly that. And in astrophysics, the astrophysicists can tell you all the many things we can look at that we're now discovering. So, I think just now, with sharing of data so possible and connectivity so great, the possibility of learning really extraordinary things, and some of which may prove to be refutable and fine, is extraordinary. I mean, we're almost at a cusp where, we're going to wake up and say, oh my God, now we see all this stuff. In some sense, it'll be exciting. In other sense, it could be foreboding to some folks.
Destabilizing, certainly.
Right. It's a complicated universe, and we live here. So, what is she telling us?
I have kind of one final big question, because you've obviously spent a lot of time at NASA, and I'm just really curious if you have a sense of NASA's end game, if they have a 1,000-year plan, or if there's like a cultural mythos that guides this exploration. Where does NASA and space exploration aim towards in the distant future? Do you have a sense for that?
Well, I'm one person, so, but NASA is an organization of people. And many of the people at NASA are brilliant engineers, because they can actually do what we've been able to do, which, may seem fairly modest, but if you look back from the lens of 1960 with no space program, or late 50s, to now, it's pretty remarkable, in that generational cycle, what we can now do. And I remember talking to one of the Apollo astronauts, this is relevant, Gene Cernan, at a meeting before he passed. And he said, so you're going to be sending a robot rover to Mars? He goes, gosh, that would have been better at the moon. And he was one of the last two guys who walked on the moon. And I thought, well, Gene, you were there. You did a lot of good work. But the rover, is like a smart dog that will do what you tell it for years. So anyway, NASA has short-term tactical goals driven by funding and inputs from, and I should say, reports from national academies that drive questions and goals. That's part of the process. And then they have the vision goals that we do as a community at NASA with different, with different mechanisms. Some are driven by the competition within NASA itself. We have 10 centers and other affiliates. I mean, there's a lot of people working with NASA. Some of them aren't even owned by NASA. They're owned by other institutions, which do great work, like the Jet Propulsion Lab owned by Caltech. So we take those exercises in the long distance strategizing of, okay, so if we learned this and this and this, what would that do for Mars? When I was the chief scientist for the Mars program, when we restructured it about 20 odd years ago, we did that kind of visioneering. We said, okay, what's an end game that's way out? Is it discovering Martian civilization? Is it understanding how another planet that was never Earth really works? What is it? And we had workshops and, town halls and other ways of gathering data, websites, and people typed in their stuff, and we digested it and looked at pathways. One of the big ones was always, could you tell if there had been or were extant life on Mars? And, what would that tell us? If we knew fundamentally, even microbially, we are just not alone. And, that's one. I mean, just what would that teach us? What if we are them, as Chris McKay used to always say, that there's been this panspermia? So that's the kind of thing we do. In astrophysics, we think even bigger to, what you can measure at the extremes of space-time and, what you would need to do that. What are the different, sort of the messenger astrophysics that would tell you about that? Some of it's not just, optical. And of course, so NASA does that routinely. We have external review boards that come in and tell us, think about this. And as a culture of an organization within government, NASA does it, in my view, pretty well. I mean, we've had administrators that really pushed us to be evocative and provocative. Dan Golden was someone like that and is still living and really wanted to push, could you use the planets of the solar system as a big lens for astrophysics and see bigger with bigger apertures, blah, blah, blah. I'm not being complete. What is the future? I mean, there was a TV show called Alien Planet that came out in 2005 that some of us worked on about sending generational craft to nearby, potentially habitable zone planets that would be bio-computationally, self-aware, that would interact with whatever's there. And that's an idea that people said, well, maybe we just need to do that. And, I had one colleague who said, well, it's a lot easier to send people if all we had to do was send our heads. So, joke. But it would save mass and energy, So, and there's AI's ways of doing that too. So I think NASA does a pretty good job. I think the community of people interested in space are in a revolutionary time of sort of the space business model with access to space and working and doing things in space, exploding across not only the billionaire space folk, but into new lines of business that will make space a happening place, not all distant deep space, but certainly out to the moon. And I think that will energize new prospects of building, architectures that will let us visionary. What if we had sensor webs connecting Earth to incoming masses from asteroids and other things, energy, space, pulses, supernovae, that would tell us about those interactions, which our planet experiences, as well as, of course, those from our parent star. I mean, these are the kind of prospects that really aren't science fiction. Now, maybe warp drive is right now, but we can sense what we can't do through vehicles that are, perhaps a metaphor for how we sailed around the planet 500 years ago, with warp drive. So I think we're pretty imaginative. The problem is that NASA has commitments to the missions we compete to do for the taxpayer dollar, in my view, and we have to deliver on those. And I think generally, it's our aim to do that. And once we put human spaceflight back into deep space, which is incredibly exciting with Artemis going to the moon, and my God, it's been a long time. That's a new wrinkle, is the bringing the humans to the place, and that I think is going to be incredibly amazing. And I suspect that
because it seems like there's almost a cosmic purpose in that. It's like the human, like people look at NASA as almost the ambassadors
historically, that's probably the case. I think that's going to change as the space exploration, at least in the science domain. I mean, there's the business domain and the kind of metrics of that, evolves. And that evolution is going to be amazing, I think. And it will open up doors for partnership science, partnership exploration, a little piece of that going to the moon with these commercial lunar payload systems that are now part of our Artemis program. But imagine that everywhere. Commercial space is the vehicle by which I actually study impact craters on Earth, because we can look at places with thousands of images and, build models of landscapes that, are, we don't have those assets at NASA because they're not part of the science priority list we have. But commercial can go after the priorities they want. And so I think that not just commercialization, but that expansion into space and with space connectivity across adaptable networks that operate as nodes, like we consider the IT networks of Earth, those things are possibilities. And, you build it and they'll come, and some visionary people will figure out how to build it. And that'll change everything. I don't think we've seen anything yet. And even the story on the moon is so vastly incomplete. People say, why are we going back? Well, because it's another freaking planet that has a whole story. It's like avoiding all of the older pharaohs' tombs because they're too hard to get to. Well, but they might actually tell us something. So we might want to study them. And that's just one metaphor. But so I think NASA right now is a brand. A lot of smart women and men have done a lot of stuff over the last 60 odd years. And I think NASA will be in more a partnership mode as we go forward. That's what our leaders have been doing really well with commercial space, commercial crew, partners in Artemis. And that brings in a bigger community, and brings community-based solutions to do things, some of which are probably better done in space than here on Earth, quite frankly. And, that'll make space more than just the cliche happening place, but a place we have to do work for our own, betterment as hominins, as people. So that's my view. I think you could argue business model-wise that has to come. It's kind of like just a natural evolution. The question is how fast, who's going to put the money in to do it? And, we could all, I'm not going to predict, but I think we'll wake up in the 30s with a different model. And, the big question to me is how fast do you want to put people way out there? Because we can do so much with robotics and, IT-enabled robotics and sensors. As one of my colleagues once said, some of the big, why don't you service some of the big telescopes? And this colleague said, because people are hot messes. You don't want to get near them. We'll contaminate them. It's better to let them be and, let very carefully constructed robots go and service and fix and extend them. Now, we did brilliantly at Hubble with the servicing missions. So, there's a place for both. And that's what I think space is going to become, a place for activity, and I'd like to see women and men on Mars. I just think it would be a visceral thing, but we can certainly do the science we've been looking to do by flying rovers like Curiosity and Perseverance and bringing samples back and drilling into the ice sheets that are very likely buried under the northern plain dusts and understanding what's there. I think there's a lot of room for learning. The thing that I think people sometimes forget when they ask about, why space is so simple. It's, because we live in it, I hate to be glib. I'm not trying to be silly, but, we do live in it. And we can't stick our heads in the sand and say, well, don't worry about that. We do have other problems we need to deal with, but we do live in it, and how it works will affect us. So anyway, that's my view. One person's view, not representative of an agency, but someone who's grown up in an agency. And, I always wanted to work for NASA, and I got another 10 or 12 years to go to get our Venus mission going with our team. So can't wait to see what we find.
I think it's audacious. There's something about, we live in Oregon and spent a lot of time in California, and there's these two very different paradigms between Oregon and California, where in the Bay Area, when you go hiking, it's very manicured and the trails are clearly marked and there's nice little, maps and trail markers and signs, and it's clearly this place where it's still really dense and really used. And the way that people go into the woods in Oregon is that you find an abandoned forest road and drive down it as far as you can, and then just kind of wander into the woods. Sometimes there's a trail. Sometimes the trail looks like it hasn't been used for, 20, 30 years. You go to these places where it's kind of clear that the high tide of industrial civilization has come and gone, because it's decrepit structures that were once something, but they're not anymore. And it's kind of a sad feeling, because you think about the amount of effort and resources that went into carving the landscape up to even put the road in there. And, the environmental considerations aside, the terrible things that happened to the old growth forests aside, there's this feeling of capability that was required to do it, and organization and just true grit. And you walk through those forests and there's kind of a sadness there where it's like, okay, we came here, we did all these things, we messed it up, and we just left it.
Kind of like the first lunar missions.
And so there's a feeling of, okay, well, we're gonna push forward on this incredibly audacious project that is beyond what we should be able to do. It's kind of like the equivalent of building the Great Pyramids, where the point is to build a cathedral that shouldn't be built on some level, because it is a demonstrable marker of ability. And I think that it can be scary to live in a world where you look around and you're like, are we less able than we used to be? Like, are we a generation that has squandered the resources that are available to us, and just kind of, there's a Russian word, it's like transirit, which is, it has this emotive quality to me of just this blind spending without any return. And I feel like space travel is one of those things where, because it organizes people into these massive groups that are focused on a singular project, you're able to strip away the conventional things that cause people to rip themselves apart on a social level. Where if you have a mission and you have giant groups of people that span continents and governments and ideologies that are all convening on an absurd goal.
Like, it's just like a really culturally healthy practice, it seems like. Like, it's just a really good exercise.
Yeah, like, it's hard for me to believe
regardless of the outcomes, almost.
Yeah, like, it's hard for me to believe that having a big project to work on isn't good for humans as a whole. Because, like, I think about it with my friends, and I'm like, the closest friendships that I have are friendships that are based on projects. We do stuff together. It's not like we just get together and, drink beers and like watch TV. It's that, okay, we're going to do this thing, and this requires us to be in constant collaboration and communication, and this is how we maintain our good friendships. This is how we build the good friendships, so that when we're 80, we have something to show for it, and it's not just all squandered. And so I think that on a visceral level is why space exploration is exciting, because we often live among the ruins of something that was perhaps once more functional.
Well, but I think you've hit it on the head. I mean, we work well in teams. And while some people have different ways of working in teams, I played goalie in hockey. Goalies are not like the people that score the goals. They're a different mindset, still have the scars and, but all that. But I think that teamwork in a project sense, whatever that project is part of our cultural development as people. And, you mentioned the Oregon, California thing. I look at the monuments humanity has made. We can all relish, marvel at them, the pyramids, whatever. And then I look at the monuments Mother Nature's made. Take a look at a 300-foot redwood. That shouldn't work on a high gravitation planet. And yet, for some set of collective reasons, they're there. I mean, they should be cherished and, prized beyond words. The great whales that are the biggest living in mass thing on our planet. To me, the spirituality of the ancient bristlecone pines up along the Sierras, my God, they've seen cycles of humanity as organized, not moving, living things. And so, we make our monuments, sometimes we leave them. Sometimes we engage in progress, if that's not the right word, but in ways that say, well, that was not the right way to go. We need to do something else. And we leave behind the detritus of that. And, Mother Nature does that. The big collision comes and reshapes, an area from an asteroidal impact. And however often they happen, that's going to change the landscape. And it might change the climate-scape. And, those are factors in how we, as people, adapt to the planet we live on, spaceship Earth, but also beyond. So I agree with you. I think teaming on projects that cross the boundaries that are artificial has led us to great things. The International Space Station, James Webb is an international project. We have Russian instruments on Curiosity. I went to Russia and we negotiated to fly one of their instruments on our vehicle. Done great. Name is Dan. It could have been Sue, but we called it Dan. It's an acronym in Russian for what it does. But anyway, those partnerships are lifelong, and they color science, I think, because I think curiosity-driven science, separated from the emotions of who gets to publish, is really it's a wonderful way of progressing. I mean, it's art in its own right, and I think Da Vinci saw that, by the way, 500 years ago, because he dabbled in all of it, and not many people did, but it's still stunning. So I totally see what you're saying, and really a powerful way of telling a story. So, we live in interesting times.
I wonder if before you go, you can give us the 30,000-foot view of what captivates you about Tonga.
So for me, I mean, I'm going to guess, I think you mean the volcano known as Hunga Tonga Hunga Pai in the island nation of Tonga. So I'm a local guy. And when I was a little kid, my grandmother, who lived to be over 100, was just mesmerized by the eruption of Surtsey off the coast of Iceland that produced a new land. And she was, worried about it. And, and I thought, wow, this is new land. Earth is making new places to go. And I thought that was really cool as a little kid. And she was, old school. I mean, lived this across many generations, including world wars, all of them. And so I was struck and actually came to study Surtsey as a microcosm of how small island volcanoes produce new land, how they erode, biology, all that stuff, which has been well studied and organized by the nation of Iceland. So it's great. Been there, mapped it with lasers and aircraft to get ready to using those technologies for Mars. It was fantastic. Been there a few times, filmed a show for Science Channel there. It was just great. So then all of a sudden, we don't have these very often. It's once every 20 to 50 years, you get new island building that lasts. And then Mother Nature gave us a gift, January 2015. There's a new Surtsey, but not in the subarctic. She's in the tropics, in this beautiful island nation of the Kingdom of Tonga, which is actually massively volcanically active with, hundreds of islands and people that understand how to live with volcanoes in the Southwest Pacific, So anyway, this island was formed and we targeted it with all the tools of the 21st century. Field trips, got students out there, measured the corals around it that were affected by the eruption, and then put together an infrastructure to study it across many international boundaries, Tonga, Australia, New Zealand, US, UK. And then Mother Nature gave us another miracle. Here is this island sitting on the rim of a submarine caldera, a hole that is a part of a volcano. And then January 15th, 2022, caldera decided to collapse. Unpredicted, not instrumented, and so 700 meters of the floor of a caldera under hundreds of meters of water collapsed into a liquid rock magma storage region. That put Pacific seawater into contact with, this hot silicate melt, saltic andesite is what it turns out to be, and kaboom, produced one of the wettest eruptions, producing water vapor up to the stratosphere to 55 kilometers, globally encircling, possibly a climate impact. We were all wondering about the total energetics, but it's probably a couple hundred megatons equivalent, a kind of eruption that on land has produced much bigger things, Yellowstone, Taupo, but this was, in the oceanic world. And so for me, this is a signal from Mother Nature that, we need to study these things. And we think this kind of process happened on Mars, when Mars had flooded areas, and maybe on Venus. and certainly on Earth, because there's lots of islands in the Southwest Pacific that show evidence of this kind of process. So sometimes Mother Nature, rings a bell for you and says, study these things, because they're going to tell you about the workings of our world, and you can apply them forward, to other places. And so I think it's a beautiful convergence, and we were lucky enough to go before we disappeared, collected rocks, observed things happening. Students went out and measured hydrothermal processes through a semester program where kids go to sea for a semester, hence semester. And it was just great to see what you can learn, as part of this international group of people that are interested in studying this kind of thing. And that was a big event in Earth history that happened quickly. Within a few hours, half a cubic kilometer of surface rock is gone, and the whole floor of the thing gone. We've been watching it ever since, using satellites, including the ones from the Canadian Space Agency. And there's all kinds of stuff happening underwater now. Trust me, there'll be more action there. Not necessarily dangerous, but still, it's just incredible. It generated a mega tsunami that washed up the sides of islands, 50 meters. I mean, this is big stuff. And so this is how the Earth works. And we don't always live to see it. But now with the tools we have today, we can live it, see it, model it, figure it out. And so, I don't know, I find those kind of things very invigorating and exciting. And, we want to figure out how they work. And
how did the inhabitants fare? Well,
the good news is this little island is, 60 kilometers from the capital island of Tonga. So fortunately, there weren't a lot of deaths, and it had been erupting in a sort of a island building style, and people from the Great Kingdom of Tonga have been watching it, as with other colleagues from New Zealand and other places, some of the experts. And so while the big explosion was unprecedented, it didn't instantly wipe out, all local inhabitants like Krakatoa in 1883 had much bigger footprint. But it was a massive eruption, producing an extremely high water vapor content eruption cloud because the water went into the liquid rock. And that's incredible. And, we're still discovering stuff about it, and it's changing, and we're using new sonar methods to study it. Not we, but a big group of people. So it's a wake-up call for how we need to see aspects of our own planet's history, as we do with earthquakes and, fires and preserving the great forests. These are just pieces of the puzzle. And for me, just, incredibly exciting.
Yeah, it's such an exciting time to be alive. I'm only as excited as I am jealous of the people that will live 500 years from now. But yeah, we're so lucky to have access to all this technology, but also all this information. It's just incredible. So yeah, I really hope we can talk to you again after you pull off this mission down the road and see just how much has changed since, it's going to be incredible.
Hopefully before 2029.
Well, we launch in 29. So that's our launch date. It takes a few years to build these things. We have 3 flight systems, giant heat shields, parachutes that have to survive sulfuric acid. To do it right, I mean, it'd be great if you could just go, but just going would not be an engineering solution. So, we have to go with our eyes wide open to everything that could happen and have our instruments work the way we've promised a lot of people. And, to be selected to do this mission with our team of women and men is, privilege beyond words. So we take it very seriously, but it will take us a little while, partly due to, just how fast NASA can fund us in times of a lot of activity. NASA's doing a lot of stuff. I mean, as is industry and other space agencies, but we'll be the first to go back to the atmosphere of Venus in a generation with the eyes of everyone riding with us. And, we want it to be as open a mission as we can make. I think DaVinci would have wanted that. So we want to honor Leonardo.
That's awesome.
It's beautiful.
Yeah.
Well, yeah, that's a great place to stop. Thank you so much for coming by and giving us your time today. And yeah, really just whetting our imaginations with what's going to come next. And yeah, it's been really, really illuminating. Thank you.
Well, thanks for having me. And I apologize. I don't think we actually talked about the topic that was initially the proposed topic of most of the discussion, the work we've recently done, but that's fine because that's just a project that's nascent and evolving as we speak, as we try to take stock of what it might mean. So I'm glad
maybe
to talk
we can
about
talk about it some other time too. I mean, I'm sure you're a busy man, but maybe you can find some time down the road to
Sure.
come back and we can get into the details about that too.
Yeah. Anyway, it's been great talking to you, really, both of you. I hope this was somewhat useful. I do tend to ramble, so forgive me.
As do we. Thank you so much. Yeah.
It's wonderful. Thank you.
All right. Have a good one.
You too. Take
Bye.
care. Bye.